Hi everyone, I am Reshma C, Assistant Professor, Department of Civil Engineering, SNIT, Adur. Today, we are going to deal with a topic that comes in the subject CE 304 Design of Concrete Structures 2. This topic comes under 4th module of 6th semester KTU Civil Engineering branch. Today's topic for discussion is circular slabs. Mainly, we are going to talk about the general design principles of circular slabs. Circular slabs in a structure are provided as per the structural or architectural needs. Circular slabs may be used for the following purposes: roof of a room or hall circular in plan, floor of circular water tank or tower, roof of pump house constructed above the tube well, roof of a traffic control post at the intersection of roads. Moving on to the general design principles of circular slab. The bending of slabs is usually different from a rectangular slab, where bending takes place in distinctively two perpendicular directions along the two spans. When a circular slab, simply supported at the edge, is loaded with a uniformly distributed load, it bends in the form of a saucer, due to which stresses are developed both in radial as well as in the circumferential direction. The tensile, radial and circumferential stress develop towards the convex side of saucer, and hence reinforcement needs to be provided on the convex face of slab. Theoretically, reinforcement should be provided both in radial and circumferential direction, but this arrangement would cause congestion at the center of slab. Hence, an alternative method of providing reinforcement is in the form of mesh, the area being equal to that required for the bigger of radial and circumferential moment. Simply supported circular slabs. Here, a slab freely supported at the edge carrying a UDL of W per unit length is shown in figure A. The radial moment distribution MR along any direction is shown in figure B. The moment varies from a maximum value of 3 by 16 WA square at the center to 0 at the edge. Circumferential moment m theta distribution diagram along any diameter is shown in figure C. The moment varies parabolically with a maximum value of 3 by 16 WA square at the center to 2 WA square by 16 or WA square by 8 at the edges. The radial shear force Fr at any radius r is given by Wr divided by 2. So, the radial moment at the center is 3 by 16 WA square. The radial moment at the edge is 0, whereas the radial bending moment at a distance r from center per unit width of slab is 3 by 16 W into A square minus R square. Likewise, circumferential moment m theta at the center is 3 by 16 WA square. Circumferential moment at the edge is WA square by 8, while circumferential moment at a distance r from center per unit width of slab is W by 16 into 3A square minus R square. The radial shear force at any distance r from center per unit width of slab is Wr divided by 2. Fixed edge circular slab. Here in figure A, slabs fixed at the edges carrying a UDL of W per unit length is shown. Radial moment distribution Mr varies from a maximum positive value at the center to 0 at a distance of a by root 3, and then becomes negative at the edges. This is depicted in figure B, MR diagram. The circumferential moment distribution diagram is shown in figure C, where m theta varies from a maximum value at the center to 0 at the edges. The moment is positive throughout the figure. So, the radial moment at the center is WA square divided by 16, and the radial bending moment at a distance r from center per unit width of slab is W by 16 into A square minus 3R square. Likewise, the circumferential moment at the center is WA square by 16. Circumferential moment at the edge is 0. Circumferential moment at a distance r from center per unit width of slab is W by 16 into A square minus R square. Using all these formulae, we shall work out a numerical in the next video. Thank you.